my name is Jason Harlow. Welcome to my V Office Hour. I'd like to go over Physics 131H1S, Term Test 1, and Question 4 from version 1. This is Winter 2011. And this is based on Night Chapter 4, Projectile Motion. Although this is a one-dimensional projectile motion question, so it's also related to Night Chapter 2. First, let's carefully read the question. A rocket, initially at rest on the ground, accelerates straight upward from rest with constant acceleration of 26.0 meters per second squared. The acceleration period lasts for time 8.50 seconds until the fuel is exhausted. After that, the rocket is in free fall. What is the maximum height reached by the rocket?
Okay, so there's two segments to the motion here. The first one is that, this is segment 1, is that its acceleration in the y direction is plus this 26 meters per second squared. And it starts from rest, I would say, so we could say that v1 equals 0. And then it gets up to some point, 8.5 seconds later, and then segment 2 is free fall. Okay, a sub y equals this negative g, okay, negative 9.8 meters per second squared. And so we need the final height. Height at the end of segment 2. End of segment 2. So I'm going to call that, if this is, say, y2 after the segment 1, I need this y3 is the height at the end of segment 2. So let's start writing out our equations here. Segment 1. Segment 1 is going to be y2 is equal to y1 plus v1 t, let's call this t1 plus 1/2 a sub y times t1 squared. Okay, we'll call this ay1 for that acceleration. We're going to set the initial position of the rocket to be 0 and the initial velocity of the rocket to be 0. So y2 is equal to 1/2 ay1 t1 squared. That's how high it gets. We don't know, and we do know the time. So that's okay. I would say t1 is equal to 8.50 seconds, and ay1 is equal to plus 26.0 meters per second squared. The other thing we know is that the final velocity, v2, is equal to v1 plus a sub y1 times t1. Okay, and then this again is 0, so we know the final velocity as well, a y1 times t1. So that's all the things we know about segment 1. For segment 2, we would say that we need the height change, but we don't care about the time. We don't care about the time taken. So we can use a variety of different things, but the equation I'm going to choose to use will be v3 squared equals v2 squared plus 2 times ay in the second segment times y3 minus y2. Okay, so the final speed squared is equal to the initial speed squared, and that's coming from the final speed of segment 1, plus 2 times the acceleration. In this case, it's going to just be negative g times this difference in height. So, and it'll be a maximum height when v3 equals 0. Max height when it stops. is when v sub 3 equals 0. So we can move down, we'll solve all this. It goes 0 equals v2 can come from here, we'll plug that into there. So it's ay1 squared times t1 squared minus, because they've got a negative g, 2 times g times y3 minus y2. Solving for that, we've got 2g y3 minus y2 equals this ay1 squared times t1 squared. We're trying to solve for y3 here, so we get y3 equals y2 plus ay1 squared times t1 squared divided by 2 times g. We also know y2 from above. We can look way up here. There it is. So we can plug that all the way down into here. Okay, so that's y3, the final height, is equal to 1/2 ay1 times t1 squared plus ay1 squared times t1 squared divided by 2 times g. So that is equal to half times the 26 times the 8.5 squared plus the 26 squared times 8.5 squared divided by 2 times 9.8.
Plugging in all of the numbers, I get 3,431 meters, which corresponds in 3 significant digits to 3430 meters in the answers. So to assess this, does it seem about right? It's 3 kilometers. If we had plugged in numbers a little earlier for V2, the velocity of the rocket once it finishes using all its fuel, I get 221 meters per second after 8.5 seconds of accelerating at almost 3g. So, and then it slows down at 1g. So I guess, yeah, 8 seconds going at sort of an average of 100 meters per second would take it about a kilometer in the first 10 seconds, and then maybe continue upwards for another couple of kilometers. So it seems to make sense. My name is Jason Harlow, and I approve this message.